Hello everybody, I'm Jacob, the Community Manager with Paradox Studio Black. Today, we'll be getting into the details of how we've worked to achieve better simulation speeds in All Under Heaven. As this will be a long and fairly technical information-dense dev diary, we'll give you some quick info and conclusions up front. With All Under Heaven, the game is about 30 to 40% bigger in terms of the amount of playable land and playable living characters. Our tech team focused on reducing simulation tick duration to keep the experience in All Under Heaven as close to CK3 as it is now. Our numbers, measured on both low specification and high specification machines internally, indicate that we have reached tick speeds comparable to the current live version. Comparable in this case means we are slightly slower in the early game, but on par or slightly faster in the mid to late game, running at speed 5 over 150 to 250 years, starting from the 1066 start date. The graph shown on screen now shows tick duration over 150 years compared to the current release version of the game. Higher means longer tick duration, therefore slower. The yellow line represents the current live version of Crusader Kings III, while the red line represents All Under Heaven. This tick duration graph shows a loss of performance in the early game, but a slight performance improvement in the long run. We've also implemented GUI, 3D graphics, and various memory usage improvements, though they were a lower priority than simulation speed itself. An important caveat here: results will vary by the world you create and the world the simulation creates around you while you play. There is no single number or graph that covers all games, hardware, and playstyles, but we aim to deliver a playable, stable, fast experience with All Under Heaven. And that's the short version. If you want more details, more graphs, and more insights into how we're optimizing performance, then listen on. Now, first we need to define what we mean when we say speed or performance. Normally, when we talk about performance, we refer to one of two categories: rendering or simulation. When developing more content for grand strategy games, we create more systems and objects to simulate over time. Graphical complexity will also increase with more development, but during DLC development, it rarely causes new bottlenecks for us. However, increased simulation demands put more load on the CPU for calculations and data transformations due to new features and systems to keep track of. This makes the CPU our most common bottleneck when it comes to optimizing for simulation tick speed. So our most common task when it comes to optimizing the code for our games is to look at where our CPU cycles are being spent and where we can be more efficient in order to keep down the average time per tick during a playthrough. This makes the time per tick measurement the most important metric for us to track throughout development, and it's the one we will be talking about most in this developer diary. So how do we get accurate measurements for tick speed when working with a complex simulation? There are many variables in play that will affect the final outcome. Examples of a variable that affects results includes graphical settings, user hardware, test length, early or late game state, background tasks, and random variation. All of these variables matter in analyzing how the game performs, but we also want to stress that most of our performance improvements are going to have a similar effect across the board for different hardware. For that reason, the most valuable test is early game tick performance on fixed hardware with fixed settings and a fixed random seed. This gives us a test that we can quickly repeat to allow us to track the tick speed trends over time for different versions of the code during development, and allows us to quickly spot performance degradations. With that said, there are some optimizations which don't fully benefit lower core hardware as much. While the early game simulation is generally just a throughput issue for the code, the in-game optimization will instead focus on trying to contain the growth in complexity. We do this by ensuring calculations scale well with a larger simulation in later stages of the game, for example with more characters or larger realms. For that reason, it's still important for us to do spot checks on lower specification machines and profiling of in-game saves to avoid focusing only on solutions that require more CPU cores to parallelize computations. One saying in software engineering and many other professions is that perfect is the enemy of good. It's a sure way to spend ages on a feature if we're determined from the outset that it has to use the most perfect and streamlined code possible. This is especially true in game development, where we often start out with one design of a feature to later tweak and modify the feature to better fit with the rest of the game and gameplay feedback for what's a fun player experience. At times, you can tell from experience where we will have future performance problems and plan for a more thought-through data architecture to mitigate that. But most of the time, the most important thing is to get features up and running to verify that they are fun. After that, we can identify which systems are not performing according to our requirements and start improving them from both a coherence and efficiency perspective. What we've described so far is our usual approach to performance work for DLC projects. However, with All Under Heaven, this all gets upended by the scale involved. Beyond having more individual features than any prior expansion, the biggest challenge for simulation tick speed is the addition of 2 new subcontinents. Both East Asia and Southeast Asia are massive additions to the world that we need to simulate for our game. This was going to be a larger challenge than any previous expansion we have ever done for Crusader Kings III. In addition to the typical slowdowns of 20% or so that we would see from unoptimized feature additions, we would now also need to deal with a 32% increase in baronies and rulers to the game. In our simulation, rulers are the smallest building block for moving the world forward. This is also linearly correlated with the amount of work the CPU must perform. This means that just by putting the rest of Asia on the map, we immediately made the game slower by an equal amount of the size increase. In the early planning stages for All Under Heaven, we set aside additional time and resources compared to a normal expansion, specifically for looking into how to make the game faster and offset the increased scope of the simulation. We also knew that we couldn't just rely on easy wins by keeping new features in line with good coding practices. This time, we had to look even deeper into what old systems we had that were holding us back. With that said, we'll now read the words of 2 of our very talented engineers, Anton and Carl Henrik, to explain in more detail how we find underperforming components in our codebase, and the methods we use to make the game perform according to the principle of gotta go fast. One approach to performance work is to look at various game systems and what it takes to simulate each system on every daily tick. We start with the most expensive system because optimizing it yields the largest impact compared to how much time we spend on it. Individual systems are also more self-contained and have only a limited number of connections with the rest of the game. It becomes easier to reason about these systems, and easier to focus on what matters right this moment as a result. Our internal tools help us visualize various game features and compare the performance impact of each one. Here's an example shown on screen now. 25 years of game time aggregated, with average time shown for the most expensive parts of the game. 63 different systems update every day in-game. 44 of them take less than 0.3 milliseconds each, so they can be ignored for now. For the remaining 19 systems, we show their names along with the average time and percentage they take each in-game day. Some game systems will always be expensive. During development, different systems may appear with larger or smaller shares of time in the chart. We evaluate how reasonable it is for this or that system to take so much time per day. There were periods when succession or situation systems were at the top of this graph, a clear indication that something excessive was happening and that we needed to investigate. Situations were being updated too frequently when nothing really changed, and succession was running a very expensive script on too many people. As shown now, both systems are now included in the Other category and are mostly fine. Characters and modifiers are typically at the top of these charts. They are the core of the game and will always take more time than anything else to calculate. This is always a difficult question for our programmers. How much faster can you make something that will always be expensive to do? Is it worth spending a few more days, or is it good enough and should we look somewhere else for easier performance gains? Average is not the only important number, however. This particular graph shows another problem. There are light orange columns, activities, sometimes spiking disproportionately, making certain months much slower than average. We want to have both a low average calculation time and no big spikes when something important happens. This is a huge advantage of these visualization techniques over just looking at the aggregate numbers. Activities will be a prime suspect for the next optimization. Now let's talk about parallel versus sequential updates. The previous graph showed the serial part of the daily tick. These next two graphs show parallel updates, however. It's very easy to reason about and develop a system with a single-threaded approach. You know things happen in order. Things are predictable and repeatable. It makes development faster, and features can be tested and balanced sooner as a result. Usually only after the feature skeleton is ready and it starts working in the game will it get connected with the rest of the game's systems, and after that we take another pass and make some of the work go in parallel. These two graphs show parallel work during a daily tick. They display the total wall clock time spent on every update every tick. It's below 20 milliseconds for each graph. It's drawn as a thick red line at the bottom of each graph. Notice how much more work gets done in total in parallel. The example is from a PC with about 20 logical CPU cores. So why not do everything in parallel? Well, we need a deterministic order of observable changes in the game for multiplayer to work, so all clients have the same game state as everyone else. Another important part is again the ability to reason about the correctness of the game. Most changes in the game have propagating side effects. A ruler conquering a new title means that another ruler is going to lose a title. Loss of a title means changes in income and military power. A ruler who gets weaker is more endangered by factions and other enemies. During any of these steps, additional events may be triggered. A strictly determined order of actions and cascading side effects is necessary to understand and predict game outcomes. Keeping that in mind, we do like to do as much work in parallel as possible. We have an internal framework that allows us to split parts of a feature into sequential and parallel steps. It was covered a long time ago in our pre-release dev diary number 36. The parallel part goes first and is called a pre-update. During the pre-update, nothing observable changes in the game. Every parallel thread sees the same visible game state, like it's frozen. In parallel, various systems can do heavy lifting to independently calculate what should be changed during the next sequential step. Everyone calculates new income independently. Every AI actor makes decisions independently. Heavy logic, triggers, and math that can be done in advance are pre-calculated. All of this is done to minimize the final amount of sequential changes. Apply already known values instead of doing math. Execute the final decision instead of making a whole decision-making process, and so on. But even during sequential updates, we still want to utilize more than one thread. This part is extra risky and complex. If we can prove that certain modifications can be done irrespective of the order of operations, or if some actions guarantee to have only limited side effects, then it's safe to do parallel work there. There's one more important note here. Only a small fraction of the game is updated each day. Our updates are separated into daily, monthly, and yearly updates. Only very few crucial systems need to be updated every day. AI movement of units is one such case where we need a daily update. Most systems in the game, however, are updated only once a month. It's a compromise between frequency and efficiency. Every day, only 1 out of 30 of all people, all construction, all epidemics, and so on are updated in the game. This spreads expensive updates equally over the entire duration of the game. Obvious drawback compared to older games? You never know for sure when it happens to you, the player. You don't know the date when you get your monthly income, it just happens every 30 days. Now let's talk more about specific changes to the game. how it applies to individual game systems. One example mentioned earlier was an expensive succession update. All Under Heaven introduces China, an enormous realm with unique succession mechanics. Lots of people compete for counties, duchies, and kingdoms, and candidates are appointed according to their merit rank and score based on the various properties of a person, their family, and events in their life. At some point, it was the most expensive system to update daily, even when you take into account that we update succession very rarely compared to other systems. That's how expensive it was. Many individually reasonable decisions led to this outcome. China has lots of titles to appoint, and the decision was to allow almost everyone to be a candidate for any county in the entirety of China. This is a quadratic problem that quickly grows out of control. What worked somewhat okay for Big Byzantium, although already a bit too slow, was no longer suitable for China. The first attempt was to change the order of operations. Can we eliminate as many unsuitable candidates as quickly as possible, so we don't have to run expensive logic and math on scoring? It's much cheaper, computationally, to find the best out of 100 than out of 4,000 people. Another obvious omission was sequential scoring. Doing appointment score math is an immutable operation and can be safely done in parallel on all people at once rather than just one at a time. Changing this to parallel scoring made it 3 times faster by itself, but it was still not good enough. It remained the third most expensive system. The third step was to go and talk with our designers about their intent behind the system. Do we really care if every courtier in China can be a valid candidate for any county? Surely we could find a compromise here. It's important that any landless ruler has this chance. Every member of a proper noble family should be given a chance to serve the realm. But what about the lowborn? Can we somehow limit their participation to titles where they personally live? This small design change halved the number of candidates, yielding large performance games while maintaining the same player experience. Players can still see important people all around the realm taking jobs, and the system still feels competitive and alive while taking even less time to calculate. It's always important to keep in mind what we want to achieve with any game system, what matters to the player, and what goals the designers have in mind. The fourth step was less impactful, but still valuable. After the previous 3 steps, most of the succession update was spent doing scripted scoring math. We were lucky to have one of our engineers get suspicious there and look deeper into the matter. It turned out to be just a single line of script that calculated holding income. One very old trigger was always fast enough, but with the introduction of governor efficiency for administrative realms, holding income is now affected by governor efficiency, which made it slower due to incorrect data caching. What was supposed to be just a simple return of a pre-calculated value turned into a whole sequence of very expensive math on demand. With the change that made cached income always valid and available, succession became so fast that it disappeared from the graph and is now included in the other category. As a bonus, any other script that was using the holding income became faster overall as well. One more way to make the game faster is to do things less frequently or not do it at all. As it turns out, the AI for barons was trying to do lots of things that made little sense for them. Barons don't have councils or court positions, yet they were still evaluating candidates for all of them. They no longer do that now. If it takes about 3 years to build a building when you only have a single holding, then you should only attempt new construction every 3 years. Barons now only attempt to start a construction every 3 years. Lots of game decisions and interactions can never be attempted by barons as they will fail various triggers for them. But what if we don't have to run those triggers in the first place? A sweeping review of availability by ruler tier for those mechanics freed even more time. And in the end, the result was not that impressive. Overall, 0.5 to 1 millisecond of total daily tick time, which can be overshadowed by random fluctuations in hardware or the current game state. Proper rulers spend so much time doing heavy tasks that optimizing barons was barely worth it. All AI decision-making already runs in parallel as well, so any performance gains there ended up being spread over multiple cores and were less noticeable as a result. Now we'll read the words of Carl Henrik, principal programmer for Paradox Studio Black, and former mentor of one Johan Anderson. Carl Henrik has been working mostly on improving performance and memory usage of Crusader Kings III. Our initial performance focus was on the game's load screen. We found that we were unprepared for the sheer volume of activity during this stage, and the only available performance measurement was debug logging, which is intertwined with all other processes occurring during this state of the game. To better analyze load time, we made a new performance tracking tool that can keep track of the entire load sequence, as shown in the image on screen. The graphs demonstrate what each CPU is busy loading or setting up, and the black portions don't necessarily indicate that a CPU is idle. They may have been too quick to show up or not included in the loading function at all. While we identified numerous areas for improvement here, implementing those changes proved to be too extensive at the time. We aim to begin enhancing these systems shortly after the release of All Under Heaven. On the subject of memory usage, however, right around the release of Cons of the Steppe, we needed to save some RAM. The minimum spec computer was having trouble running the game, and this had previously been researched by our console porting team. Bringing the entirety of Crusader Kings III to modern platforms is an impressive feat, and having access to their work meant that we could make these memory improvements fast. One particular improvement was the memory usage for tooltips in the game, which was surprisingly high. Bringing this one change to the PC version saved several gigabytes of memory usage. With this memory improvement in place, we also needed to look at code performance. Early measurements showed as much as 1.5 times the performance degradation from our earlier DLC, Cons of the Steppe. Our programmer's approach prioritizes code improvements, while other team members who specialize in design focus on elements such as scripts and character action frequency within the game. To monitor optimization progress and identify development-related issues, we run our performance analyzer daily for 100 years. This is done both on a high-spec computer with 32 processors, 64 gigs of RAM, and Windows 11, as well as a lower-spec machine with 8 cores and 16 gigs of RAM. From the graphs produced by this performance analysis tool, we can investigate any of a multitude of systems for performance issues. Once a system has been identified and the relevant slow code tracked down, we can start making improvements to it. Most of the time, we find that things updating other things that don't all need to be updated. For example, in the performance graph for the pre-update phase, script variables were one of the top users. In saved variables, script variables, we narrowed the check for variables that need to be updated, as they can time out. So instead of checking around 500,000 variables, only a few hundred need to be tested for each tick. This change made the category disappear entirely from the graph. Setting aside simulation performance for a moment, graphics tend to be one of the largest performance categories for games. But even with the latest map updates, Crusader Kings III is not significantly impacted in this area. To improve graphical performance, we've introduced adaptive frame rate. This new setting benefits computers with fewer than 10 processors by subtly lowering the rendering frame rate when there is minimal screen activity. This should be enabled with the low-quality graphics preset. Adaptive frame rate works together with the maximum FPS setting, which has a new default option called Display Refresh Rate. Previously, disabling VSync and leaving the max FPS turned off led to a significant decrease in performance due to the frame rate being uncapped by default. For optimal performance with minimal rendering impact, enable adaptive frame rate and set the maximum FPS to 30. The updated map and other improvements have increased the amount of detail for the graphics processing unit to process. This may lead to longer frame processing times and a lower screen update rate, potentially making the interface feel less responsive. While this does not affect the daily tick rate, as the CPU and GPU work in parallel, we plan to investigate methods of better balancing this workload. Many optimizations are straightforward and easy to reason about, but sometimes you find something small and innocent looking that can drag you into a deep rabbit hole. There's a function that does a few checks and runs a relevant script if those checks are passed. This is about 30 lines of code, but contained enough performance issues that improving it took over 2 weeks of developer time. The slowest line of code was a call that basically just checks that the script scope matches what the trigger or effect is expecting. Making some trivial improvements yielded no results, which simply indicates that the compiler automatically did that work for us. Even though the function is not inherently slow, the sheer volume of scripts executed per tick makes this the most resource-intensive aspect of the entire game. The actual problem with this line turned out to be that to check the scope, each trigger generated a 120-bit flag field, and compared that with a 128-bit flag field generated from the scope. Replacing this with simply comparing the numbers of scopes greatly improved performance. Unfortunately, triggers and effects can accept multiple kinds of scopes, so ultimately, if the initial check fails, the bit flag test is still necessary as a fallback, but this is already a great improvement. In most cases, triggers and effects return the scope number, but there's also a concept of links that only return scope bit flags. We ended up spending 2 days going through all of these classes and adding the missing functions. The trigger and effect also seem to suffer from cache misses, and adding a cache prefix helps a bit more here, but this was just one line of the function. We have an in-game script profiler that we use extensively trying to improve the performance of scripts. This should only have a performance cost when it is used, so it required a bit more investigation. We need to remember the file name and the line of the file for the script, and this particular data type had an inefficient implementation to store that information, so that helped quite a bit. However, this efficiency is still redundant when not in use. Therefore, employing an in-place new instead of the default constructor made this line acceptable. While time-consuming, each step of experimentation, testing, and profiling ultimately proved invaluable due to the significant performance improvements achieved in the process. Sometimes, making things simpler also makes them faster. Every character has a lot of opinions about other characters, and the strength of each opinion can change over time. The system that tracks opinions cleverly cached the current opinion value and calculated the future date when this opinion changed 1 point. Now, to get a hold of the current opinion value between characters, it just needed to be found in the cache, and all opinions checked each day whether it was time to step. This check was in a sorted list, so only the opinions that were about to change needed to be considered. Unfortunately, after each step, the new date needed to be reinserted into the list, so this improvement was becoming more expensive as we added more characters. Ultimately, the calculation is simply a multiplication with a change rate constant and an addition, so getting rid of the cache and just calculating the opinion on the fly was much faster than maintaining a sorted array. Now we'll read the words of Don, senior programmer on CK3, and the coordinator for the code discipline on All Under Heaven. Additionally, he's also the design feature steward for China Mechanics specifically. This puts him in a good position to talk about how we worked on performance from a design and script perspective. Our script files, present as text files in our game, are responsible for a large portion of our game's mechanics, and offer great power to our designers as well as our modding community. But with that great power comes some responsibilities, and also a very big downside. Paradox script is not as fast as the equivalent C++ code, and it can be fairly easy to accidentally make something slower than is needed. To counteract that, we have added some tooling in recent releases that allows us to more easily find slow scripts. The script profiler, for example, is accessible in-game already when in development mode. Using these tools, we went through almost all script files in the game looking for performance gains. We reshuffled trigger orders, simplified structures, used equivalent but slightly faster micro-optimizations, and a lot more. We apologize to modders in advance that might prefer we keep our scripts largely unchanged, but we adjusted a lot while optimizing things for All Under Heaven. We also looked at our most used triggers and effects and compiled our C++ side of these as well. Sometimes we even created new triggers outright. A good example is the aptly but awkwardly named "is available quick" trigger. This new trigger allows us to check a number of already existing availability status checks in one go, because we discovered we check them together a lot. They result in functionally equivalent logic to calling each of these separately, but under the hood it is just one single, smarter, faster block in C++. Similarly, we have added shortcut options to a number of script list generators for often used filters, speeding up script with only text tweaks. We also investigated and implemented an automatic script order optimizer, which shuffles the order of script execution according to weights, to gain performance by stopping execution earlier. We ultimately decided to leave this script optimizer disabled for now, because we were not always seeing enough consistent performance improvement from it. This makes it a good example of something that you can encounter when working on performance. One performance improvement can eat into the gains of another one. And in this case, our other script optimizations snipped away the biggest gains of this tool. We may yet enable this if we deem it statistically useful in the future. For the curious of you, you can enable the basic version of it by running the game with a simple command option flag. Sometimes we simulate things we shouldn't, things that do not matter, or things that will not change as frequently for certain character types. A lot of our script logic did not have easy tooling to adapt AI frequency in a smart way. For example, most character interactions were considered as frequently by a baron in Iceland as by the Emperor of China. So we adapted a number of our systems, interactions, decisions, and more to be able to configure tier-based frequencies for AI consideration. This also provides us with a statically defined way to say how frequently a specific tier of ruler should consider something, but also, very importantly, when they never should. For example, we have the releases tributary interaction for nomadic Mandala and Wanua rulers. Should barons or counts consider this? No, never, because they are mechanically unable to do so. Dukes? Maybe. Not very important for them. Yet in our old interaction definition logic, we would have to do a check, and it would get checked every year by every ruler, with a relatively expensive script check. With tier-based AI frequency definition, we can eliminate this check, and put this interaction in a bucket that never gets checked by a count or a baron. As an important bonus point, this also allows us to make things be considered more frequently for higher tier AI rulers without losing performance due to lower tier characters, making the game AI more responsive when it matters. We added this style of tier-based frequency configuration to almost all character interactions, decisions, activities, and great projects, on a total of about 550 types of things our ruler AI can consider to do. One of the more popular performance mods out there to make the game faster is the population control mod, which starts eliminating people when the world's population reaches a certain number. Now, we haven't done exactly that, but we have tried to combat the underlying issue. We accumulate characters that don't do much, and after a couple of hundred years, these characters can count in the tens of thousands. So we went and reduced or eliminated a bunch of sources of characters that generate boring, useless, random, or invisible characters that then linger in guest pools. The sideline of courts of barons and counts, and that take up space and cost performance. At the same time, we keep the more interesting characters that have a bit of history around longer, and we draw them into events more, often replacing a randomly generated nobody. This allowed us to trim the useless fat that accumulates in long-running games, reducing the strain that even relatively light non-ruler characters leave on the simulation systems. So let's take a look at where we are at now, a couple weeks before release of All Under Heaven at the time of this writing. We did initially measure nearly a 1.5 times degradation in daily tick rate, and set a goal to not be more than marginally slower than our previous release. We've added significantly more map area, and with it, significantly more characters. With just a couple weeks until release, we are in the final stages of development and implementing daily changes. We've made significant performance improvements, with the game now running significantly closer to the current release's speed than our previously set tick rate target. This has been confirmed on both high-end and low-spec computers used for testing. While your mileage may vary, we're hopeful we can get it a little bit faster than that once the dust settles from the final stretch of All Under Heaven's development. Play fast. And now, some closing words about minimum hardware requirements from Jimmy, the technical director for Studio Black. First of all, we are amazed at the work the team has done with performance for this very technically demanding expansion that is All Under Heaven. As part of our performance review for this expansion, we revisited our minimum hardware requirements, specifically the CPU baseline. As has been mentioned in this dev diary, after months of optimization work, we've recovered nearly all of the slowdown seen during early development. From an initial big increase in daily tick duration at the start of development, the game now runs comparably to our current live version, with some fluctuation between the early and late game, even with the expanded map and heavier simulation in play. And these tests have been done on both high-end and low-end hardware. In other words, this update to hardware specs isn't about unoptimized code, it's about ensuring the game runs reliably for everyone. During extensive testing done by our hardware lab, we could see that older CPUs like the Intel i3-2120, released back in 2011, struggled to behave predictably under heavy load, especially alongside systems with just 6 gigs of RAM. This represented our original 2020 minimum spec. Impressive longevity for hardware that's nearly 15 years old. But to ensure a consistent experience, we're now updating the minimum CPU recommendation to an Intel i5-750 or AMD FX 4300 paired with 8 GB of RAM. These configurations are still modest by today's standards, but they provide the stable and predictable performance needed for what Crusader Kings is today, 5 years after its original release. And with that, our dev diary about performance draws to a close. As always, thank you for listening. If you want to stay up to date on everything Crusader Kings III, then please like this video and subscribe to the channel. We'll see you next time. You know, I was originally going to release this one on Tuesday, but it turns out if you ask a bunch of programmers to talk about what they've been doing for the past year, they'll take you up on it. Every time I looked at the script for this dev diary, it got at least 1,000 words longer. It got to the point where late Monday evening, I'm looking at it and realize there's no way we're getting this out on Tuesday. So, apologies for the delay.